The main focus of this first unit in physics, our introduction to mechanics, one of the main focus points, let's put it that way, is the describing of the motion. Over the past week and a half, we've been talking about those concepts that we use to describe motion: position, velocity, acceleration. Remember, if we remember back 2 videos ago when we first talked about introduction to motion, introduction to mechanics, so there were some ground rules. And the first ground rule was we were just going to describe the motion, not talk about its causes. And that's really what we're doing here in this first unit. Another way that we can do that is by using graphs. Namely, in this case, we're going to start with our time versus position graph. And like the subtitle says, representing one-dimensional motion graphically. So, first definition, time versus position graph. Details the location of an object relative to a reference point over a specified period of time. Hopefully, you read that and go, duh, because that's the name of it, time versus position, right? We talked about that position, the location of an object relative to a reference point, and if it's time versus position, it's going to tell us the location of that object over a specified period of time. When we're making time versus position graphs, we want to put certain measurements in certain places. Namely, we want to make sure that time is the independent variable. It's on the x-axis. Whenever we use the lab quest, whenever we're making motion graphs, time almost, I can't think of any time when it isn't, is going to be on the x-axis. That may seem weird if you were creating a time versus position graph, because most of you probably wouldn't make time the independent variable, the one that you change on purpose. But by putting these measurements in certain places on the graph, namely on one axis versus the other axis, we can get more information out of that graph than just the position of that object over a specified period of time. Starting off, here are 2 time versus position graphs for these 2 swimmers shown in the picture to the right. Swimmer 1 wearing the white cap, swimmer 2 wearing the yellow cap. And the graph to the left details the position of those 2 objects over a specified period of time. Now, you might look at this graph and go, y-axis doesn't say position, it says distance. I got this graph out of a book that's at a lower level than the class that you're taking right now. So they're not real picky about those things. But what I'm going to do is I'm going to take this, I'm going to take this graph and this picture, and I'm going to pull it out of PowerPoint, and I'm going to throw it in here into my notebook software. So the first thing we need to do is we need to fix this graph. Hold on, some sizing issues. There we go. First thing we got to do is we got to fix this graph. We're going to get rid of distance here and call this position. It's a more detailed description of what this graph is showing us. It's showing us where this object is relative to a reference point. The reference point most likely being the starting line of this race, wherever it was, and then it shows us where those objects are over specified periods of time. What I want you to do is, going back to the PowerPoint, there are 4 questions that go along with this graph. So I would like you to take a couple of seconds, either hit pause, or if you just can do them really fast, and answer these 4 questions in relation to this. Hold on a second. Sizing issues. Answer these 4 questions with the help of that graph above. So if you would please, sorry, keep that there. Hit pause. Answer these 4 questions, then we'll come back in a couple of minutes. First question, what is the position of swimmer 1 at 20 seconds? I'm assuming that most of you wrote this. Hold on a second. Let me get my yellow pen because it'll show up better. I'm assuming that most of you wrote this, 20 meters. However, remember, position is a vector quantity. It tells us both magnitude and direction. If we're talking about one-dimensional motion, there are 2 places that are 20 meters away from the starting line. So we have to specify which one. So the proper answer here should be positive 20 meters, because it's on the positive side of the reference point. How far ahead of swimmer number 2 is swimmer number 1 at 20 seconds? So we move it up. Oh, sorry. My bad. Yikes. Same concept, but I was reading the wrong time, so it should be positive 40 meters. My bad. How far ahead of swimmer number 2 is swimmer number 1 at 20 seconds? So I look at the 20-second line here, okay, and I see that swimmer number 1 is at positive 40 meters. Swimmer number 2 is only at positive 20 meters. So in this case here, I would say 20 meters. No real need to put a positive on that because the how far ahead is asking you for distance. If you remember back to our very first video, distance and position tell us both the location of the object. Position tells us where it is in reference to the or where it is in relation to the reference point. But distance, how far ahead of swimmer number 2 is swimmer number 1, all we need is a distance there. It's not asking where is swimmer number 2, it says how far ahead. So no need for a positive negative there. What is the displacement of swimmer number 1 from 10 to 40 seconds? Hopefully you remember displacement, the change in position, is calculated by doing x final minus x initial. If we look at this graph, 10 to 40 seconds. So 40 seconds is going to be our final position, swimmer number 1. So that's right there. Probably should have used a different color. That's right there, right? So the final position is going to be positive 80 meters minus the initial position. So at 10 seconds, swimmer number 1 was right there. So initial position would be positive 20 meters. We do the math and we end up with positive 60 meters. Important for the plus or minus sign on that one? Yes, it is, because displacement is a vector quantity. We not only want to know how far that swimmer went in that time interval, but which way did that swimmer go during that time interval. And then the last question, which swimmer is faster? How can you tell? Most of you, I hope, would get the fact that swimmer number 1 is faster. And just from this graph, the only way that we can tell is the fact that swimmer number 1 goes a farther displacement, has a greater change in position during the same time interval. Sorry, bad writing. Same delta t, right? She goes a farther displacement within that same time interval. Therefore, that's faster, right? Remember, faster is a representation of velocity. Velocity is change in position over change in time. Hopefully we got these 4 questions without too much trouble. Maybe a little bit on the vector scalar thing, or how I worded things, or how I described things using those terms that we introduced earlier. But I think most of you probably could look at that graph and answer these questions. Let's take it one step further, going back to our PowerPoints. Right? I mentioned earlier that it's important to make sure that we put time on the x-axis and position on the y-axis. Because if we do so, what we'll find is that we can get more information out of that graph than just where this object is over a specified period of time. If we look at the slope of a graph, or we look at the slope of this graph in particular, let me go here. Okay, there's that. So I'm going to make myself a little time versus position graph, just like this. And if I do that, I want to make sure that position measured in meters is on the y-axis, and then time measured in seconds is on the x-axis. And I'm just going to draw myself a graph that looks something like this. So if we take a look at the slope of this graph, we define slope as rise over run, or the change in the y variable over the change in the x variable. Hopefully you all know that from math class, and I think you all do. If we apply that to this graph specifically, if we look at our rise axis, we're measuring position on our rise axis. But more importantly, at least for where we're going with this, is that on the y-axis, we have a unit that's measured in meters on the y-axis. On the x-axis, we're measuring time. That unit for time is equal to seconds. So if we look at the units of the slope of this line, remember, in math class, slope is just a number. But here, this graph is made of measurements that we've taken from the real world, some aspect of the universe. So it's not just a measurement here, it's not just a number on the slope, it's actually telling us something. The units are meters per second. Hopefully you remember from our last from the last couple of videos that in meters per second we use to measure velocity. So the slope on a time versus position graph is going to tell us the velocity of that object. On a time versus position graph like the ones we were just looking at, right, they're straight lines. What can we say about what do we know about the slope of a straight line from math class? Hopefully you remember the fact that a straight line has a constant slope. So these two swimmers are moving at constant velocities. Is that realistic? Probably not, but it's the first graph we ever looked at least in class. Okay? So these two swimmers are moving with constant velocities. Also, if we go back to question number 4, right, which swimmer is faster? How can you tell? Before we said number 1 was faster because it goes the farther displacement during the same time frame. But if we take a look at it from the standpoint of, of the slope, right? If we go back and look at the slope of swimmer number 1's line versus the slope of swimmer number 2's line, swimmer number 1 has a steeper slope. That's another way that we can tell that she's going faster. Straight lines are easy. But if we take a look at, not that one, this one, if we take a look at a graph like this, okay, slope of time versus position graphs for a graph that looks like this. Okay? Hopefully you remember from our Unit 1 discussion, this is a quadratic relationship. It's a graph that looks like a parabola. Mathematically equation-wise, there should be an x squared term somewhere within that trend line equation, which isn't showing on the screen, but that's okay. Also, just to be consistent, right, if we look over on the y-axis, it's saying distance, but it's not telling us distance, it's telling us position. If we look at the motion of this object, hopefully you would see that this object is going farther in a certain amount of time, but it's not going the same distance or the same displacement, within an equal time interval. If it was, it would look like a straight line, but it's not a straight line. If we take what we just learned about the slope of this graph and what's happening to the slope of this curve, well, the slope of this curve is increasing, right? More specifically, the slope of the line tangent to that curve. I think we're all familiar with that term. A tangent line is a line that hits a curve in one spot and one spot only. So if we take a look at this tangent line, that's the line that's tangent to the curve at that point, and then there's a tangent line at that point, and then there's a tangent line at that point. The slopes of those tangent lines keep increasing, right? If we go back to this one, come on, too far, right? Shallow slope, steeper slope, steepest slope. On a time versus position graph that's curved, the slope of the tangent line tells us the instantaneous velocity. Remember from our previous discussion, instantaneous velocity, what is happening right now. The slope of the tangent line is going to tell us that. On a curved graph, if we know the slope of the tangent line, we'll get the instantaneous velocity. Those of you that are taking calculus right now, you're going to examine this concept pretty deeply. I guess I don't know what Mr. Rusha does, but Mr. Miller used to do it a lot. The fact that the slope of that tangent line, we can learn through the derivative of the function that's representing that curve. If you're not in calculus, don't worry about that. We're not going to do it in here. We're just going to talk about slopes of tangent lines, talk about it conceptually mostly, but get to that idea. So on a time versus position graph, there are 3 things that we should be able to tell. First thing that we should be able to tell, the instantaneous position of an object, where that object is relative to a reference point at a specific moment in time. Second thing we should be able to tell is the displacement of that object, the change in its position over a specified period of time, looking at where it is at t final versus where it was at t initial, and we can find both of those things out from a time versus position graph. Third thing we should be able to tell from a time versus position graph is the velocity, and more specifically the instantaneous velocity. What is that object currently doing? And we do that through the slope of a tangent line. All right, that brings us to the end of our first motion graph, time versus position. But in order to accurately describe an object, right, we have to answer 3 questions. Where it is, when the answer to that question being position, but then also what's it doing right now? And that takes us to time versus velocity graphs. First, definition. A graph of the instantaneous velocity of an object over some specified period of time. And once again, hopefully you get the idea of duh, right? That's what a time versus velocity graph would tell you. Okay? Sorry, I try to keep consistent up here. On the first page, I had time versus velocity. The title of this page, I have velocity versus time. I try to be consistent and make it time versus velocity because, like I'm going to show you here in just a second, we want time to be on the x-axis. Once again, just like in the time versus position graph, time on the x-axis, it's our independent variable. Velocity is the dependent variable on the y-axis. When you do the lab quest, time is always the x-axis regardless of which graph you're looking at. The lab quest, or the motion detector of the lab quest, measures time, velocity, and acceleration all at exactly the same time, or simultaneously, so time is always the x-axis. And I think that most of you have seen the function on the lab quest where we can pinpoint a dot on that graph and it'll show us the time and it'll show us the position and velocity at that simultaneous time because the time axis is the same for all of those graphs. Something to remember, velocity is a vector quantity, so it has to tell us both magnitude and direction. And I think that going through the acceleration on incline lab, I got to talk to a lot of you about the whole idea between the positive and the negative velocity. So here's what I want you to do first. Just on a piece of scratch paper, or some of you may have printed these out already. If you did, well, I guess what I can do is I'll take away the answer slide when I post them online, so you don't have the answer right in front of you. But here's a time versus position graph. Taking what you learned in the previous discussion about time versus position graphs and what you can figure out, I want you to see if you can sketch me. Don't worry so much about actual numbers, although you can probably figure out the numbers from this graph. But just real quick, give me a sketch of what the time versus velocity graph for this corresponding time versus position graph would look like. I'll give hit pause, give you a couple seconds to figure it out, hit play, and we'll come back with an answer. On this set of axes, I went and put the time versus position graph that I originally gave you, different color. It's orange now instead of blue like it was on the previous screen. Whatever, don't worry about it. And then I put the time versus velocity graph down here at the bottom. Here, in the beginning part of the time versus position graph, the position of that object is constant. It's not going anywhere, right? Remember, position tells us where it is relative to a reference point. If it keeps coming up the same answer, the y-axis in this case telling us position, if it keeps coming up 2, 2, 2, 2, 2, that object isn't going anywhere. Also, if we take a look at it from the things that we can tell about the time versus position graph, the slope of this line, slope of a horizontal line, is 0. And that means that during this time frame, the velocity is also 0. Then we have a part right here in the middle where we have the position of this object increasing at a nice regular rate. Okay? It keeps getting farther and farther and farther and farther away from the reference point, if the reference point is 0, which in this case it always is. But more importantly, at least from the velocity standpoint, is the fact that we have a nice constant slope right through this time. Okay? That means that the velocity is constant. And in this case, if you do rise over run, you can figure out that the velocity of that graph during that time is a positive 1 meter per second. So I show up here on, on the velocity graph being the light blue represented by the light blue, we see a horizontal line at positive 1. Now, that horizontal line doesn't mean that it's standing still. Horizontal line on a position graph means it's standing still, but a horizontal line on a velocity graph means that the velocity is constant. It's moving at a constant rate. Then, up at the end, we see that the position is holding steady at 5 meters. Once again, no change in position, there's no velocity, right? Velocity, our definition of velocity being change in position over time. If there is no change in position, there is no velocity. Also, the slope of this graph, or the slope of the graph during this portion of it, is 0. Horizontal line, 0 slope. So once again, our velocity drops back down to 0. Okay? These two spots on the position graph represent the same kind of motion or the same velocity of motion. There's zero velocity. Even though it's in different spots, it's still zero. On the velocity graph, we represent that with horizontal lines on the x-axis because the y values of the graph during that moment in time are both zero. Now, some of you may be thinking, well, wait a minute. I went from a zero velocity and I just jumped up to a velocity of 1 meter per second. In reality, the graph can't look like this. It can't be real jagged. It has to have some kind of curvature as you go through here, right? And same thing up at the top. It has to have some kind of curvature as it goes through here. This is the first time versus velocity graph that we're looking at, so we're going to hold on to the curvature, okay? But you'll notice that on your lab quest, you don't get real sharp, jagged portions like this. They're always, the position graphs are always curved. The velocity graphs, sometimes horizontal, but generally they're changing, and we'll look at more of those as we go along. Question number 2, same thing. Here's another time versus position graph. I want you to take and see if you can sketch, or if you want to get more detailed with it, put numbers on a time versus velocity graph for this time versus position graph. I'll give you a couple seconds, hit pause, sketch yourself out a little time versus velocity graph. We'll come back and talk. There's the corresponding time versus velocity graph that goes along with the blue time versus position graph. Remember we said that any horizontal line on a position graph is representing an object that is standing still, has no velocity. So there are two portions of this graph that are horizontal, from 0 to, I don't know, about 0.5 seconds, I guess. And then from 3 seconds to 4 seconds, we have horizontal lines. So velocity-wise, those graphs, or velocity graph is 0 at that point in time. It's a straight line along the x-axis. Now, from 1.5 seconds to 2 seconds, this object has a constant velocity. How do I know? Well, the position keeps increasing at a nice constant rate, but more importantly, the slope of this graph is constant during that time. If you do a little rise over run, you should see that the slope of that graph is 2, so we have a constant value of 2 through that time. Here's where it gets a little more complex than the last one we just did. During this portion in time, from 2 seconds to 3 seconds, if you look at the slope, it's a constant slope, so it's a constant velocity, but it's a negative slope, right? If you look at the position graph, this object starts off not moving at all, moves farther and farther and farther away from the reference point because the y values on the position side of this, using blue to represent position, right? The y values on the blue graph keep getting bigger, 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 bigger. It's moving farther away from the reference point. But if you look at the position, or the y values of the position graph during this point in time, between 2 and 3 seconds, those y values are getting smaller, 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 smaller. It's moving back closer to the reference point. It's moving in the negative direction. It's still on the positive side of the reference point. The position values are still positive, but the slope of the position graph, which tells us the velocity, is negative. So we represent that with the negative velocity. Do a little rise over run, it's -2 rise over +1 run. So it's a -2 velocity, right? If we talked about the speed of these two motions, remember speed just telling us magnitude, the speed of these two motions is exactly the same. They're moving just as fast, but one's moving forward and one's moving backwards. They're always on the positive side of 0, but one's moving in one direction, one's moving in the other direction. Same speed, different velocity. And we represent that velocity with the positive and negative. And that's why we have some positive velocity values and some negative velocity values. Then we already stated from 3 to 4, horizontal line, slope equal to 0, velocity equal to 0. And then during this section right here, if you do, it's a negative slope once again. It's a negative, constant negative slope. Little rise over run, -2 over a run of +1 gives us a -2 velocity. Okay? Those are hard, especially from the first time that we've done them, but the more and more that we do them, I think you'll see that we can get more and more out of these graphs than just what is stated in the title. And an example of that comes from here. So I'm going to take this, and grab this, get out of PowerPoint, because sometimes writing in PowerPoint isn't so hot. And I'm going to shrink this up a little bit so we have some room to work with. And I'll expand you out. And we get this, okay? On a time versus velocity graph, we said we wanted to always make sure that time is on the x-axis, velocity on the y-axis. So if we do the same thing that we did for the position graph and take a look at our slope, right, and especially the units of our slope, we said that velocity is going to be on the y-axis. So we want to have meters per second there, right? That's what we use to represent the velocity of an object. Okay? On the x-axis, we have time. Seconds on the bottom. Hopefully you remember from past couple, from our previous recordings that meters per second over seconds can be simplified down to meters per second squared. But more importantly, that's the unit that we use to represent acceleration. All right? The slope on a time versus velocity graph will tell us the acceleration of that object during that time. Okay? Just like the slope on a time versus position graph tells us velocity, the slope on a time versus velocity graph tells us acceleration. So let's head back here and let's take a look at these two slides. Okay? First, on the y-axis, once again, got this from an old book. Is this the speed on the y-axis? No, it's not the speed. It's the velocity. How can I tell the difference? Well, if the y-axis has a positive part and a negative part, even though we're not showing the negative part here, it still has a negative part of the y-axis. That means that there's positive velocities and negative velocities, or positive speeds and negative speeds, although should have stuck with never mind. Positive velocity, negative velocity. What did we say the positive or negative stands for in velocity? Tells us which direction. So this graph is showing us not just speed, not just how fast, but also which way. If we look on this, right, the slope of the time versus velocity graph tells us acceleration. The graph that I'm showing you right now, the one on the left, it has a constant positive slope. It's a straight line. Okay? Constant positive slope means that this is a constant acceleration, a uniform acceleration. How do I know? Well, look at the speed. It keeps getting faster and faster and faster and faster because the y values keep going up and up and up and up. But more importantly, they go up at a nice constant rate. Every 1 second that goes by, this velocity goes up by 4 meters per second, and 4 meters per second. So if you think back to the preliminary questions on the acceleration on the incline graph, it asked you about a uniformly accelerating object and how fast was it going after 4 seconds compared to 2 seconds. Well, and if we look at this graph, right, at 4 seconds, this object was moving at 16 meters per second. At 2 seconds, this object was only going at 8 meters per second. So after twice as much time, or increasing the time by a factor of 2, we've increased the velocity by a factor of 2. Second graph looks like this. Once again, we're not representing speed on this graph, we're representing velocity. Okay? Beginning of this graph from 0 to 10 seconds. The velocity is constant. Remember, position graph, this means the object is sitting still. But on the y-axis, if this is velocity, that means that object is moving with a constant speed in the same direction, positive 5 meters per second. But then, all of a sudden, the y values start going down, 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 down. Okay? That object is still moving in the positive direction because these velocity values are still positive. However, the value keeps getting less and less and less. If we go back to our definition of acceleration being the change in velocity over the change in time, right? V final minus V initial over T final minus T initial. Apply it to this graph, right? The V final, let's call V final right here, okay? After, it's a tough time, okay? Why don't we go from 10 to 15? Okay, so between there and there, right? So this will be v final, right? Because it's the second one. What's the speed at that point in time, or the velocity at that point in time? Let's say positive 2.5 meters per second, minus the initial velocity, which was positive 5, right? All over the time frame in which that occurred. The final time is 15 seconds, minus the initial time, which is 10 seconds. So you end up with negative 2.5 over positive 5, right? Positive 5. And that gives us a negative number, more specifically negative 1/2. There's a negative acceleration occurring here. Remember we said, if the velocity is positive, which these values are because they have positive signs, we're above the x-axis, and a negative acceleration, that object is slowing down. And that's what's happening in this graph. Those velocity values keep getting closer and closer to 0. All right. Ooh, let's go here. Sorry. Next thing I want you to do is, this is going to be, oh, sorry, one mention back with these graphs on the slope of the time versus velocity graphs. Okay. Once again, those of you that are taking calculus, you'll see that if we take the derivative of a velocity graph, you'll get the acceleration function. Also, when you start talking about double derivatives, if you take the second derivative of the position graph, you'll get the acceleration function. Just making connections if you're in calculus. If you're not, don't worry about it. All right, here's that same graph that we did. We said that by putting certain measurements on certain axes, we can get more information out of this graph than just what's there. Example, see this red triangle I drew here? Okay. I can look at, I filled in the space between the x-axis and whatever function we graphed on this section. Okay, we call this the area under the curve. Okay? Those of you taking calculus, this is represented by the integral of the function that we're graphed on, that we're putting on our axis. Those of you not taking calculus, don't worry about that term. Those of you that are in calculus, I'm pretty sure you haven't gotten there yet, but probably the second half of the year. Okay? But if we just look at it from a geometric standpoint, we can find the area of that triangle. Hopefully you remember that finding the area of a triangle, base times height divided by 2. If we look at the base of this triangle, right? Now, let me do this. I'm going to get this so I can write a little more. Okay. Grab that and bring it over into my notebook so I can write a little bit more. Ooh, that's very large. We need to squish this down a little bit. Okay. All right, let's get all that other stuff out of the way. And there we go. Okay. If we look at this red triangle that we filled in the space between the x-axis and the function itself, the graph that we made, the area underneath the curve. If we check out the base of this triangle, that would be right here. And if you look at the units on the x-axis, it's 4, right? Except, remember, this isn't just numbers on this graph, it's actual measurements. So it's not just 4, it's 4 seconds. And then the height of this triangle, right, looks like this, and it goes from 0 to 16, but it's not just 16, it's 16 meters per second. If we take those numbers and plug them into this formula for the area of that triangle, okay, so the area is equal to the base, which was 4 seconds, times the height, which was 16 meters per second, all divided by 2. You do a little math, okay? 4 times 16, you could figure that out on your calculator if you want to, okay? But more importantly, if you look at units, this seconds and this seconds are going to cancel. And we're left, when we do our math, with 32, but it's not just 32, it's 32 meters. So if we take a look at that and go, okay, well, what does that mean? 32 meters is a distance. More specifically, it's a displacement. So if we look at the area between the x-axis and the curve itself, that will give us the displacement of the object during that time frame. So, we got here, here, okay? And this is just going to run us through what we just did, but more importantly, Where is it? Come on. There it is. The area under a time versus velocity graph is going to tell us the displacement of that object during that time frame. So I'm going to take this and I'm going to give you this graph again. Okay? And, oh, missized. Let's do that. Let's get out of there. And what we'll do is we'll just grab this graph and go into Notebook. All right. And there it is. Okay. So if we look at areas under the curve, we don't always have to do it in just one step. Here, this first part isn't a triangle, it's a rectangle. Right? If we have a horizontal velocity graph, we can't fit a triangle in that spot. Well, I suppose we could fit two, but rectangle would do it in one step. Then here, let's see if this will work. Right? It's not sizing me right, which doesn't make me happy, but let's see if we can squish this over. Apparently not. But you get the gist. Now here, hold on. Undo, undo. Let's see if this will work. Let's see if I can actually draw a triangle in this spot. There, there. Try and keep this as straight as I can. And there we go. There's my triangle. Okay. So now I have a rectangle filling the first part of this area and a triangle filling the second part of this area. Go ahead and take a couple of seconds and calculate what the area of that rectangle would be and then what the area of that triangle would be. And we can figure out what the displacement of the object is during that time frame. Hit pause, come back in a couple minutes. I'll do the calculation for you. Go. So I calculated the area of the rectangle, base times height, calculated the area of the triangle, base times height divided by 2, get these values, add these together, 50 plus 25 gives us a positive 75 meters. That's the displacement of that object during that time. All right, one last one, pretty complex, but we'll go with it, okay? So here is a time versus velocity graph. And first thing you should be able to do is you should be able to describe what's happening to the motion. So why don't you take just a second, go through in your head and go, okay, what kind of motion is this representing? Hit pause, come back in a couple minutes, go. Describe the motion of this object from this time versus velocity graph. Here's how I would do it. Starting off, this object is standing still. How do I know? Velocity is 0 at the beginning part of time. Then there is a constant positive acceleration or a uniform positive acceleration. The velocity of this object is increasing, 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 increasing in the positive direction, making some connections back from the relationship between velocity and acceleration. The velocity values are all positive during this time. How do I know? They're above the x-axis. The acceleration is positive during this time. How do I know? It's a positive slope on the time versus velocity graph. Positive velocity, positive acceleration, increasing in speed. During this moment in time, velocity is constant, not changing at all. Constant 3 meters per second, going the same speed. During this section of the graph, the velocity is decreasing in the positive direction. Once again, making connections. Positive velocities, they're still on the positive side of the x-axis. Negative slope, negative acceleration. Positive velocity, but negative acceleration, slowing down. Oh, that's supposed to be an arrow. Slowing down. Ooh, writing is slowing down. Yikes. Hold on 1 second. Let me do this. Okay, let's take this, and if it ever decides to do it, there we go. I'm going to take this graph, get you out of here. Oh, that's not what I wanted. That's the next picture. Come on, there we go. And there's my graph. Okay, so description standpoint. Let's get a little smaller. Widen this out. There we go. Okay, so first, during this section, right, we have positive velocities but negative, or sorry, and positive accelerations. And we already talked about how we knew that. And that means we get a speeding up effect, right? During this section, we have positive velocity, but we have zero acceleration. How do I know? The slope of that graph is zero at that time. That gives me a constant velocity, right? It's still moving in the positive direction, same speed. During this section, okay, I was getting to it at the end, the velocity values are still positive because they're all above the x-axis, but the acceleration values are negative. I switched that up. Hold on. For you OCD people, no names, but positive velocity but negative acceleration because the slope of that velocity graph is negative during that time, and that gives me a slowing down effect. If you look at your velocity values, they keep getting closer and closer and closer to zero. That's slowing down in the positive direction. Then, during this section, okay, the velocity values are all negative because they're all below the x-axis. But the slope of that graph is also negative, and that means we have a negative acceleration. If we have velocity and acceleration with the same sign, even though they're both negative, this is speeding up. It's just speeding up in the other direction. And if you look at the y values during this time, they keep getting more and more and more negative. That's a speeding up effect. So speeding up, constant velocity, slowing down. We already talked about these two sections, or we kind of made mention of them before. The two purple sections here and here, velocities are equal to zero, so there's no movement at all. That object is at rest. Right? I guess we should probably do that, right? Zero velocity and zero acceleration because the graph is flat, and that's at rest. Okay. Then during the orange section, the velocities are negative because they're below the x-axis, but the acceleration is negative because it's a negative slope. That gives us a speeding up just in the other direction. All right, let's take this one step further, and let's take a look at this picture. We said that if we found the area under the curve, we could tell us the displacement of that object during that time. Okay? So take a couple seconds. I know the time values are a little bit bigger on this graph than they have been on the previous graphs, but that shouldn't stop you from being able to do what you're supposed to be doing. And let's calculate what the area under that curve is. So go ahead and hit pause. Then you can start working on some calculations, and then come back and I'll do the calculation for you. Go. because these are displacements, they should all have positive signs on them. And that's going to be important when we go here to this triangle. Right? Remember, this isn't just a distance, or it isn't just a length like in math class. This is an actual measurement. And the height of that side right there is going to be -2. That's important because it's giving us displacement. So that means we end up here with a negative displacement of 100 meters. That just means it went back, turned around, and started going back towards the reference point. All of these displacements during this section are all positive. That means that it's speeding up, going at constant velocity, and slowing down, but it's still always going in the same direction. It's always getting farther and farther away from the reference point. But during this section, the purple part, that velocity or displacement being -100, means that it turns around and went back to where it started. So you put these all together. Let me do that real fast. Plus 150 minus 100. And you end up with a total displacement of positive 462.5 meters. That means it ends up 462.5 meters on the positive side of the reference point from where it started. It doesn't actually say that it started on the reference point. Remember, this is a velocity graph. Just because it started at 0 doesn't mean that it started at the reference point. But calculating the total displacement of positive 462.5 meters means that it ended up 462.5 meters on the positive side of where it started. Okay? And we'll never know where it started because it just doesn't tell us. All right, let's wrap this up. Okay. Time versus velocity graph. 4 things that you should be able to tell from the time versus velocity graph. Let me get this out of the way. First, instantaneous velocity. Where is that object at a specific moment in time? That's just the y value of the graph for a corresponding x value. Average velocity of an object over time. Here, we didn't really talk about this in the presentation, but if you go v average, right, you're looking at v final plus v initial divided by 2. Just taking the average of something, right? So if you know what the final velocity is and you know what the initial velocity is, you can calculate the average just by taking a quick average of them. The instantaneous acceleration, how much the object's velocity changes at a specific moment. That's the slope of the tangent line of that velocity graph. And then the displacement, the change in its position over time. That's going to be the area underneath the curve. Hopefully, a lot of the stuff that we talked about in this presentation makes sense based on the graphs that we've looked at in our 2 LabQuest labs that we've done so far. And then also there's a couple other assignments that we'll do in class that reinforce these ideas. But remember, the focus of this first mechanics unit is the description of motion. Graphically describing that motion goes a long way to really understanding what's going on. And if you can understand these graphs and describe motion from those graphs, you have a good understanding of those concepts. We'll work on it some more in class. If there's questions, bring them with you. I'll see you guys in class.